Alright, so bases. So what's a base? Bases are caustic and bitter to the taste. They're electrolytes and they react with acids to form neutralized solutions like salt and water. Bases are slippery to touch and they're mostly ionic compounds of metal plus hydroxide ions. Some examples of bases that you might be familiar with are bleach and toothpaste. Strength of bases. Bases can be strong or weak just like acids. For a strong base, you're going to have the hydroxides of group 1 metals and of calcium, barium, and strontium. Basically, strong bases are the hydroxides of alkali earth metals and alkali metals, so group 1 and 2. For a strong base, you're going to fully convert into hydroxide ions in solution, so you're going to have a unidirectional arrow for these reactions. For weak bases, you have ammonia and organic amines. An organic amine is when one or more hydrogen atom in ammonia is replaced by a hydrocarbon. Weak bases do not fully convert into hydroxide ions in solution, so the reactions are going to be reversible, indicated by a double arrow. Types of bases. Like acids, bases are categorized by the 3 scientists that define them: Arrhenius, Bronsted-Lowry, and Lewis. Arrhenius bases are defined by the ability to make OH- ions in solution. The most specific definition of a base is the Arrhenius definition. So bases just increase the concentration of hydroxide ions in solution. With the dissociation of sodium hydroxide in water, you're going to get Na plus and OH- ions. Sodium hydroxide is a strong base because it's a group 1 metal of sodium. This means that it's going to fully dissociate into its ions for this reaction, so you have a unidirectional arrow. For Bronsted-Lowry bases, they're defined by the transfer of H+ ions from an acid to a base. A Bronsted-Lowry base is a proton acceptor, and water can be both a Bronsted-Lowry acid or a base. Here we have 2 examples of water acting as an acid and a base. For the first one, we have water plus ammonia is going to give you ammonium and hydroxide ions. For this reaction, water is acting as your acid and it's giving up 1 hydrogen ion to form the ammonium cation. In this case, since ammonia is a weak base, you're going to have a reversible reaction because it's not going to fully transform into its ions in solution. In the second case, you have water plus hydrochloric acid gives you hydronium and Cl-. For this, HCl is your acid and it's going to transfer 1 hydrogen ion to form H3O+. Your conjugate base here is Cl-, and that's going to be weak because HCl is a strong acid. Lewis bases are defined by the ability to donate an electron pair to form a covalent bond. Anions can act as Lewis bases to form covalent compounds. In this example, we have boron trifluoride plus F- gives you Bf4-, where F- is your Lewis base. Lewis is the broadest definition of a base. So here are some helpful vocabulary terms for this chapter. Amphiprotic is a compound that accepts and donates protons. An amphoteric is anything that can behave as an acid or a base. The oxides of aluminum are amphoteric. So for the first example, we have aluminum oxide plus hydrochloric acid gives you aluminum chloride and water. In this example, aluminum oxide acts as a base and HCl is your acid, so the transfer of protons is going from HCl to H2O. In the second example, we have aluminum oxide plus sodium hydroxide gives you a complex ion. For this reaction, aluminum oxide is acting as your acid and sodium hydroxide as your base. So for these 2 examples, it shows us that aluminum oxide can act as both an acid or a base, so it's amphoteric. Conjugate acids and bases, so they differ in the presence or absence of 1 proton. When an acid loses a proton, it makes a conjugate base, and when a base gains a proton, it makes a conjugate acid. For a strong acid, the conjugate base is weak because the ionization is unidirectional and favors the right. For a weak acid, the conjugate base is going to be strong because it has a reversible reaction. So here we have 2 examples of both strong and weak conjugate bases. For example 1, we have hydrobromic acid plus water is going to give you hydronium and Br-. In this case, hydrobromic acid is your acid and water is your base, so since HBr is a strong acid, it's going to lend a proton in a complete transfer of protons to get you H0+ and Br-. Since HBr is a strong acid, according to our strong acid list from the previous video, you know that your conjugate base is going to be weak, so Br- is your weak conjugate base. For example 2, we have nitrous acid plus H2O gives you hydronium, and NO2-. For this, nitrous acid is your acid and water is your base. Since HNO2 is a weak acid, the ionization is going to be in equilibrium. It's going to favor the molecular form, but the conjugate base can reverse the reaction. In this case, since you have a weak acid, you're going to have a strong conjugate base. The behavior of OH-. So in an oxyacid, OH has an ionizable hydrogen atom, so it's acidic. In combination with group 1 metals and calcium, barium, and strontium, OH can form bases. And with COOH, it's going to be acidic. OH in an organic alcohol can also be acidic, as shown in the example below. So that's basically all that you have to know for bases. So thank you for watching, and I hope you enjoyed this informational video.